We discuss in this video about presenting relations with the help of Boolean matrices. We discuss about relations in this lecture. So, relation is really defined on the basis of two sets. So you have A, B being sets, and really R is nothing else than a subset of this Cartesian product of A and B. So we call this R to be a binary, and it's a binary relation because it's between two sets A and B. So it's a binary relation over A and B. And we can define R simply as a subset of this. So we can just say, look, we have this particular element, and you just enumerate these elements, or you give some sort of set of rules that define them, where A is in A and B is in B. And so you describe all of these elements that are in relation R. So we often write A, R, B to denote the fact that element A from A and B from B are in relation R to each other. We also define right away the inverse. So this is the inverse relation. So the inverse relation is defined to be a relation over B times A, and it's really the set of elements BA with B in B and A in A in such a way that A R B. So in other words, whenever you have AB in relation R, you are going to place BA in relation R minus 1. So R minus 1 doesn't do anything else than just switching the position of all elements. Wherever you had an AB in R, you will have a BA in R minus 1. We also define a composition of relations. So if we have relations R, relation R over AB, and we also have a relation S over sets B and C, then we define the composition. So a composition or composed relation R circle S, I just denoted like this. So this is going to be a relationship over A times C, and it consists of all the elements AC with A in A and C in C in such a way that there is an element B in B with A R B and B R C. So what this means is that the composition is all those pairs AC in such a way that there is an element B in such a way that AB is in relation R and BC is in relation S. So in other words, you can go from A to C by passing through an intermediary node or intermediary element of B. And when I say passing through, I mean you pass from A to B via relation R, and you pass from B to C via relation S. So I hope this is intuitive enough for you. And another thing that I want to do is the power relationship. So if I had a relation over set A times A, so in this case, we don't have two different sets, but it's just set A, and R is a binary relation over set A. So in this case, we define the power relation in an inductive way like we had before. So R to power 0, this by definition is going to be the identity relation, meaning this relation only has pairs of type AA with A in A. So this is the identity relation. And power 0 is defined by default to be the identity relation. And then in general, we will have r to power n plus 1 to be r to power n composed with r. So this is going to be for all n greater than or equal to 0. And the intuition really for r to power n is in general that elements a and b are in relation r to power n. If you can go from a to b in n steps, and each step is really via a relation connection. So you will go from a to the next element, let's say a prime, and a prime are in relation r. Then you go from a prime to the next one, also through relation r, and so on. And you do that in n steps. So that's the intuitive idea behind r to power n. Finally, I also define the complement. So if you have a relation r, this time in general, over a times b, and we define the complement to be really all the elements a, b, such that they are not in relation rb. They are not in relation r to each other. So this is also the same thing as saying this is exactly the complement of r with respect to the full set a times b. So this is called the complement of r. And again, the intuitive idea for the complement is that you are going to collect in the complement relation all those elements that are not present in R. So R is really, R composed is really the all the remaining elements that are not in R. So once we have these basic definitions in place, I can now introduce the basic concept I wanted to cover in this lecture, and that is how do you present a relation via a Boolean matrix. So that's the definition I want to give here. In your lecture notes, this is definition 2.34. And what I'm going to say is we have two sets, two finite sets, and I'm even going to enumerate their elements. So this is set A, consisting of elements A1, A2, all the way to AM. And I also have set B, a finite set consisting of n elements, and they are exactly these B1, B2, Bn. So just by saying this, I'm assuming that we have the elements of a ordered with whatever criteria we have in mind, but we, just by writing that this is element 1, by default, we are assuming that in some sense, when I have to think about A, this is going to be the first element, and that's going to be the second element. So just by indexing them, I'm imposing a partial order on A, and just by indexing the elements of B, by default, I'm introducing a partial order on B. And it doesn't have to be more sophisticated than this. It's just the way, the order in which I'm listing these elements. It doesn't have to capture any deeper properties about the structures of A and B. And now, if I have a relation R on A and B, so in other words, R is a subset of A times B, then I'm going to associate to it. So I will say associate to R, a Boolean matrix, which is going to characterize R. So this Boolean matrix, I'm going to denote it by MR, and this is going to be a matrix, so Rij, and it's going to be of type M times N. So it's going to have M rows, just like as many elements as A has, and it's going to have N columns, as many elements as B has. And the elements are defined like this. Rij is going to be, so it's going to be 1 if element AI is in relation R with element Bj. So if the ith element of A is in relation R with the jth element of B, I'm going to denote that by 1 on the position ij of this matrix. And if they are not in a relationship, then I'm going to denote this by 1. And I hope it's clear to you that just by writing this matrix, I'm essentially enumerating all the pairs A, B that are making up the relation R. So just to give you an example of how this goes. So if I have set A to be, for example, X, Y, Z, and I have set B to be, for example, A, B, C, D, E, and F. And for example, I can have the relation R to be these pairs, XA, YC, YF, and ZE. So another way of writing this is just by saying that, look, I have X in relation R with A, Y in relation R with C, Y in relation R with F, and Z in relation R with E, and nothing else. So that's the definition of R. And so then to describe R as a Boolean matrix, I'm going to have, so A has 3 elements, so I'm going to have a matrix with 3 rows, and B has 6 elements, so it's going to have 6 columns. So this is going to be a matrix 3 times 6. And I'm going to have 1 row corresponding to X, and 1 row corresponding to Y, and 1 row corresponding to Z. And I'm going to have 1 row corresponding to A, another to B, to C, to D, to E, and F. So these are not part of your matrix. I'm just writing them to help with your intuition. So I'm just checking here. I see that X and A are in relation R. So I'm just checking X. I'm representing all the things about X on the first row, and all the things related to A on the first column. So I'm going to indicate by 1 the position of X and A. They are in relation R, so it's going to be 1 here. Then I have Y and C. So on the second row and third column, I'm going to have a 1 because Y and C, they are in relation R. Then we have Y and F. So I'm going to have 1 on this position. And then I have Z, E. So Z and E, I'm going to have a 1 here. And everything else is 0 because R only has 4 elements. In this matrix, I'm going to have only 4 positions in which I have a 1. All the other ones are 0. So I'm just now filling in all the other positions. And that's going to make up the matrix MR corresponding to relation R. Like that. Yeah. Maybe I just move this one a little bit to the right, so we have the right position. Right. So there are now a number of properties I want to prove about this mapping from relations to Boolean matrices, and I formulate several of them in the following lemma. This is lemma 2.36 in your lecture notes. Again, like I had before, I'm going to say, hey, let me take 2 finite sets, A consisting of elements A1, A2 all the way to AM, and set B corresponding or consisting of elements B1, B2 all the way to Bn. And I'm also assuming that I have relations R and S. So R and S are 2 relations over A and B. And so then I have a number of properties. And the first one is the matrix corresponding to R is equal to the matrix corresponding to S if and only if R and S coincide. So in that sense, the matrix completely characterizes the relation. We only have the matrices being equal if and only if the relations are equal. Second point, remember in the previous lecture we have defined a partial order on Boolean matrices, and this property says MR is smaller than or equal to MS if and only if R is included into S. That property says the matrix corresponding to the union of R and S is simply equal to MR plus MS. And the fourth property says a matrix corresponding to the intersection is MR in element-wise or Hadamard product, element-wise multiplication or Hadamard product between MR and MS. The fifth one says the matrix corresponding to the complement of R is the complement of this Boolean matrix. And remember, we have defined this in the previous lecture. And finally, the sixth property is that the matrix corresponding to the empty relation is exactly the zero matrix, and this is a matrix of type Mn. And the matrix corresponding to the full relation A times B is exactly the one matrix, obviously of type M times N. And really, there is nothing difficult about proving this lemma, and I'm going to leave most of them to you as an exercise. I'm only demonstrating one of them, point 2, but the other ones could be good for you to prove at home. They are not deep, but they are going to provide an opportunity for you to practice with going between relations and their associated Boolean matrices. But here is how to prove point 2. So we have that MR is smaller than or equal to MS. And remember, this is about this partial order on Boolean matrices, and this we have defined in a previous lecture. And we have defined it by this one holds by definition if on all positions we have this relationship. So I'm sorry, this is an S. So MS on IJ, and this is true for all I, 1 to M, and all J from 1 to N. And this was equivalent, we have made this observation also last time, so this is equivalent with MR IJ being 0 or MS IJ is equal to 1. And it only takes 1 minute of thinking why this is true, but this is easy to see. And this is true for all I and J. And so this is equivalent now with saying, look, since you have 0 on this position, by the way we have defined these Boolean matrices, it means that AI and BJ, they are not in relation R. And the fact that they are not in relation R, I'm going to indicate with, crossing out R with oblique line. So I and J, AI and BJ are not, because I have 0, are not in relation R. Or, obviously, AI and BJ are in relation S. And this is true for all I and J. So this is equivalent with the fact that if AI and BJ were in relation R, so this would imply right away that AI and BJ would be in relation S. And again, this is perhaps not completely obvious in a moment, but take 1 or 2 minutes to think about this, and you will realize that this is true. This is the based on how implications are defined. It's either not this one or that one, and that's exactly what we have on this side. And so what this means now is that this is equivalent with AI bj belongs to R implies right away that AI bj belongs to S. So, and this is true for all I and j. And obviously, this is the same thing as saying that R is included into S. And that's exactly what property 2 of this lemma was saying. So this concludes our proof of this property. There is another set of results that I want to prove now, and this is really about the inverse relationship and about the composition of relations. So here is how it goes. This is lemma 2.37 in your lecture notes. And what it says is, just like before, I have sets A consisting of elements A1, A2, AM, and set B consisting of elements B1, B2, Bn. I also need in this lemma a third set, set C consisting of elements C1, C2, all the way to CP. And I'm going to have relation R over AB and relation S over BC. So with this setup, there are two results I want to formulate here. One is the matrix corresponding to the inverse relationship of R is exactly the transpose of the matrix corresponding to R. And the second property I want to mention here is that the matrix corresponding to the composition relationship, R composed with S, is exactly equal to MR times MS. And this is the usual matrix multiplication over Boolean matrices. We have defined this in the previous lecture. And I would like to prove this. I will prove just the second point. The first point is really easy to prove. I would encourage you to solve it by yourselves. But I will show the second point. So first, I just want to fix the types of these matrices. So a matrix corresponding to R and S. Remember, R composed with S. This was defined to be a relationship over A times C. So the matrix corresponding to RC is a matrix of type M, how many elements A has, times how many elements C has, so M times P. And the type of R, of the type of matrix MR is M times N, and the type of matrix S is N times P. So this identity has a chance of really holding if we just think about the dimensions of these matrices. And so remember, these are Boolean matrices. All the entries are just 0 and 1. And so I'm going to start thinking about the entry ij of this matrix being equal to 1. And I do this for some I, for some arbitrary I between 1 and M, and J between 1 and P. So exactly the way I have it in the dimensions of RS. So I'm going to say, hey, this entry ij of this matrix is 1. Then, I mean, by definition, this is true if and only if AI is in relation R composed with S with Cj. So element AI of A and Cj of C. And this, by the definition of what a composition is, it means that, so this is equivalent with, there is a K between 1 and N in such a way that AR is in relation, AI is in relation R with BK, and BK is in relation R with CJ. And so this is equivalent with, there is a k between 1 and n in such a way that really the entry of this matrix at ik, so that takes care of this part, this is equal 1, and the entry in matrix, I'm sorry, there was a mistake here, this is not an R, it's an S, so I'm fixing this. So this is S, so the matrix S at position K and J, that's a 1. And having them 1, this is equivalent with, and I'm going to write it and then I comment. This is only true when we work on the Boolean algebra B2. So this is equivalent with this product MR IK times MS KJ. This is equal to 1. And this is true based on how this product was defined. The product is 1 if and only if both elements are 1. And so this is now equivalent with, again, I'm just writing this and then I comment. So this is equivalent with the sum of MRIK times MS AJ, sum of all the k's from 1 to m, is being equal to 1. And again, this only holds for the Boolean algebra B2. And the reason is this sum was defined to be 1 if and only if at least one of these elements that are being summed up is 1. So that's exactly what we are saying. This sum is 1 if and only if at least one of the elements in this sum is equal to 1. And so this now obviously means that, so this is equivalent with the product matrix MR times MS, if I take the ij element, which is exactly what this sum is, if this is equal to 1. And so in this way, we conclude, so consequently, we have just concluded that this matrix M corresponding to R composed with S is equal to MR times MS, which was the claim that we wanted to prove. Just one more point I want to make about relations over a given set. So in other words, relations that are being presented by square matrices. So in this last part of this lecture, I'm going to take just one set A, consisting of elements A1, A2, AM. And just to have it as you have it in your lecture notes, I'm going to erase this M and I'm going to say N. It doesn't make any difference, but you have it like this in your lecture notes, so I'm going to keep it like that. So A1, A2, all the way to AN, and I'm going to have a relation R over A, which also means that the Boolean matrix associated to R has type n times n. And there are a few things that I want to define here. One is the identity matrix. So the Boolean n times n identity matrix. So this is, as you might expect, this matrix IN is the one having 1 on the diagonal and 0 everywhere else. And that's obviously a matrix of type n times n. So what this means, the identity matrix, it means that really two elements are in relation IN with each other, if and only if A equals B. So that's why we call it an identity matrix, because it really captures the identity relation. And I would like to define now the transitive closure of relation R. So the transitive closure of R. So this is defined like this. It's going to be denoted by plus, and is going to be consisting of relation R, union with R squared, union with R to power n. And I'm also defining the reflexive transitive closure of R. And this is going to be denoted by R star. And it's almost exactly the same, except that I'm also adding the identity matrix IN to relation R plus. So if you like, this is IN union R squared all the way to Rn. And this is a little bit unusual in terms of how transitive closures and reflexive transitive closures are typically defined, meaning that typically they are defined as infinite unions, so also of powers higher than n, and in fact powers going all the way to infinity. The reason why we stop at power n has to do with something that will only become clear from next week on when we discuss about automata. And just to anticipate a little bit, this is about your ability to go from one state to another one by not visiting any state more than once. And if you have only n states and you don't want to visit a state more than once, then obviously you only can visit up to n state, going from any state to any other state. So all of these might be making very little sense at this point, but maybe you'll come back to this comment once you see about automata. But this is maybe, if you have seen transitive closures in another context, you might wonder why do we keep it like this? But we keep it like that because it's the only thing we need in terms of finite automata. So there is one final result I want to formulate about this, and that is your lemma in the lecture notes. This is lemma 2.39. And what this lemma says is I have a set A, just like before, and R, so set A as above, so consisting of n elements, and I have a relation R over A. And in this case, I have the following properties. Property 1, the matrix corresponding to the identity relation is exactly the identity matrix. And second point I want to make is that the matrix corresponding to the power relation, remember we have defined this in the beginning of this lecture, is exactly obtained by taking the matrix corresponding to R and raising it to power m. And this is true for all m greater than or equal to 0. The third property is that m, the matrix corresponding to the transitive closure of R, is in fact exactly the matrix mr. If you like, to power 1 is going to become clear in a second. Why do I put 1 here? Plus mr raised to power 2 plus all the way mr raised to power n. And so remember, r plus was defined here is the union of all these powers of relation r from 1 to n, and the result is saying this is going to be true also in terms of matrices. The matrix corresponding to this is a sum of these powers of the basic matrix mr. And finally, this should be no surprise now, the matrix corresponding to the reflexive transitive closure, R star, is in fact In plus the matrix mr to power 1 plus the matrix mr to power 2 and all the way to the nth power of this matrix. And I'm going to leave this lemma unproved to prove it is really just a similar type of calculations like we have done before.